So we're going to look at, there's a relationship between, well, the amplitude of waves and the intensity that you experience from them. And there's also the inverse square law. So we're going to go intensity versus amplitude and try to explain how that's related. And we're also going to talk about inverse square laws. So inverse square laws are found all over the place in physics, and it's got to do with the way really that energy is transferred throughout space. Not necessarily just energy, but the way that sources emanate in fields, okay? So you find inverse square laws like in the Newton's law of gravity, or you'd find them in like the way that the intensity of lights dims as you move away from them or towards them. And you also find it in the power of sound, okay? So the first thing we'll talk about with waves is this little nugget right here, that intensity is proportional to the square of the amplitude of the wave, okay? So first we got to talk about what do we mean when we're referencing intensity. So intensity is the power per second, okay? So let's just remind ourselves of this, okay? Now this is just a linear wave, but these represent energy traveling through the wave, right? And the higher the amplitude, the more energy that these carry, right? So if we think about it, if we were to increase the amplitude, oops, I want to keep the same wavelength though. Let's see if I can fix that. Okay. So we'll say this is wave one and this is wave two. Say the amplitude is like essentially doubled here, okay? So we'll call this amplitude is equal to 1, and here we'll say amplitude is equal to 2. So if you remember, we said that you get simple harmonic motion, SHM, when the restoring force, right, is proportional to the amplitude or the distance from the neutral, right? So what that means is if this is some sort of elastic medium, like a spring or a slinky or something like that, the farther that this point gets stretched away, the larger the restoring force to send it back the other way. We also said that the period would be the same for a given frequency or a given amplitude. So if this represents, you know, the drawing out of that swinging pendulum or whatever, what we're really talking about is a higher amplitude. And we remember that amplitude did not affect the period, right? So this means something. What this means is when this point crosses back across the neutral, all right, seeing as how it had a higher force on it and it's traveling, it's accelerating for a larger distance, it's going to have a higher velocity when it crosses the middle, okay? So these points will have a higher velocity when they cross the middle. And if we remember that in real life in a mechanical wave, this rope has mass associated with it, we could say this, that the kinetic energy associated with the mass on that rope is equal to 1/2 its mass times whatever velocity it is squared, okay? So what that then means is that the energy carried by, say, a single wave pulse is going to be proportional to the square of the amplitude, right? In all cases. Why is that? Because the velocity is faster. The velocity is higher the higher that the amplitude is, right? And since velocity is tied to the kinetic energy of this moving mass, as we increase amplitude, we increase the energy associated with each wave pulse. So in a case where amplitude is doubled, all right, so here we have 1 squared, which is of course just 1, but here we have double the amplitude, so we have 4. If we were to triple the amplitude, we'd have 9 times the amount of energy per wave, etc. Okay, so energy is related to amplitude. Now, we don't often use this directly. We most often talk about it in terms of intensity being proportional to amplitude, but this only makes sense when we're talking about waves traveling in 3 dimensions, okay? So we're going to take a step beyond this. We're going to think about this, this idea. So let's say we have some source vibrating, Okay, so some source of sound, some monopole or whatever. And we know that the sound is traveling outward in 3 dimensions. Okay, so you have spheres around here, right? We're going to talk about these spheres. And basically, the sound power is spread over an area of the surface of the sphere. Does that make sense? The sound power is spread over the surface of a sphere. So when we talk about power, and it doesn't just have to be sound, I shouldn't just say it's sound, but any energy source emanating out in 3 dimensions, you measure its power divided by the area that it's over. So what you get then is you get watts per square meter, right? So power, remember, is joules per second, right? Per square meter, okay? So you've got watts per meter squared, right? So the word we have for this power divided by area is called intensity. So intensity is power over area. And just so we don't confuse that with amplitude, let's do that. Power over area, okay? So going back up over here, right? If we say these have the same frequency, right? They have the same frequency. We're getting then the same joules per second, right? But the intensity is lower if the amplitude is lower, and the intensity is higher if the amplitude is higher, right? If all other things are kept the same, okay? So from the fact that joules factor in here, right, we were able to sort of link joules to amplitude back over here, then it should make sense that if energy is proportional to the square of amplitude, seeing as how all we're doing now is keeping all this stuff the same and looking at the power, right, and if frequency is the same, right, we're getting the same number of wave fronts per second, okay, then we should be able to just make that leap and say, okay, if energy is proportional to the square of amplitude, so must intensity be proportional to the square of amplitude, okay? So that sort of, I think, is the intuitive way to understand this. You can very likely prove it with calculus, but we'll maybe leave that for the experts. All right, so I want to look at a 2D example first here, okay? So let's say we drop a rock in a pond or something like that, okay? This isn't going to be perfect, but I think it's going to build up to an understanding that we want to have. So let's imagine these waves move outward from the source. Okay, so as we get farther and farther out, and these are representing like what are called wave fronts if you want. And we'll study them in a little more detail later on, but oops. We'll study them in a little more detail later on. But if there's some, power coming out of the center here, or there's some amount of energy per second if you want, okay? So there's some power coming out of here, okay? You can think about the fact that that power is spread over a larger and larger area the farther we get out from the center, okay? And so just intuitively then, if you double, so let's say that's R, that's 2R, and all the way out here is 3R, right? Meaning radii, okay? Bigger and bigger radii for this circle, okay? We would say that the circumference, or the distance around here, is what that wave power is spread over. Does that make sense? Okay. And one kind of way to think about this is, so if the energy is spread over double the radius, then that's double the circumference, right? Because we've got 2 pi r equal to the circumference. If we double r, right, if we go 2 there, the circumference doubles. If we go 3 there, the circumference triples. So in other words, the energy is spread over a larger and larger circumference, okay? And what will happen is a big amplitude here will be about half there and about a third there, okay? Does that make sense? Because the energy is spread over a larger and larger region, okay? So as we move out, right, our amplitude drops, and therefore the overall power per, or intensity, I should say, the overall intensity as we get out gets lower and lower and lower, okay? So then if we think about the intensity of each of these points, right, it's going to be proportional to, so here, let's go with where r equals 1, okay, where r equals 1, we'll say intensity is equal to 1, right? Here, though, I is equal to So the amplitude is halved, right? So back to where we were talking, if the amplitude's halved, okay, then we've dropped to a quarter, right? So this is your kinetic energy of your matter going up and down. So when you double R, right, you have the velocity that that wave's going to have, right? Because you have the amplitude of the wave here, and then when you get to the third R out, right? Okay, so here it's 1. Here it's a half squared, right? The half and the m stay the same across both. So half is 0.25, so that's like a quarter. And then here you have 1/9. So I think that's like 0.111. So yeah, so you get like 0.1111. So you get this kind of like law that basically states that the intensity is going to decrease at a square to distance away from the center. Okay, and we're going to look at this in one more light. But before we do, we can just make a simple rule. We could say that the intensity is going to be proportional to 1 over the square of r. Okay, so this is the basic form of inverse square laws. Okay, so I want to look at this in a slightly different way. We're going to look at it in terms of 3D now. Think about it in a different way. So here's a source. I have a thing that draws circles, but I think I'm just going to be, it's going to take too long to mess with it. So we're going to try to imagine now that we're in 3D. So these represent spherical shells at various distances out from the center. Okay, so you can imagine there's spheres out into space from some point source of energy. Okay, so we've got R, we've got 2R, and we've got 3R, and so on. Now imagine, right, that an area on the surface of here, like this, okay, and we'll draw it back to the source. Okay, so at this point we could test the intensity. Okay, we can say that I is equal to 1. Okay, now watch as we extend these lines out. Okay, so I'll use my straight line drawer here. Back ones. Okay, when I get to the second radius here, so I want that to be green. Okay, when I get out to the second radius, this will actually cover an area that's 4 times larger, right? So when I'm at 2r, I get an area 4 times larger. Now, why is that? Well, the surface of a sphere is equal to 4 pi r squared, right? So we just take, this rule should also follow then for just a fraction of that surface. But I mean, you could extend this for the whole surface if you want. If you double the radius of a sphere, you quadruple the surface area, okay? And now when we triple it, we go to 3r. Okay, when you triple it, well, when that happens, you go to 9 times the area, right? So you got 9 A's to deal with, and so on. And that's just your, basic geometry of the way that 3D space works, right? So your area has gone from A equals 1 to A equals 4 to A equals 9, while your radius has only increased at, singly, 1 by 1 by 1 by 1. Now the amount of power in all of these shells is the same, right? The amount of power is the same. I mean, if this is a 100-watt source, you have 100 watts, spread over one area, or you have 100 watts spread over 4 areas, or you have 100 watts spread over 9 areas. All right. So this is another way to kind of understand that inverse square law. The area that the sound is spread over is always increasing at a square to distance around these spherical shells, or these spherical shapes. Should have drawn this a little more curved. It looks too flat, but you get the point. And from that, right, we just draw this same thing that we found before when thinking strictly about the amplitude. The intensity is equal to 1 over the square of r. Okay, so again, we're pulling, using a slightly different way, this inverse square law for intensity out of this, right? And just keep in mind, obviously, right, that intensity is power over area. So power in watts over area, right? So if we say have a 100 watt source, right, our I here is 100, right, watts per meter squared. Here, it's only 25 watts per meter squared. And here it's, I don't know how to do that. Hang on. Like 0.111, it should be 11.1. Okay? And if we were to graph that out, what would our graph look like? Well, you'd have your standard inverse square graph. Okay? You're never going to get to a point where sound power is 0 or okay, but you get this kind of a thing, right? Where you have oh, sorry, that's not power, that's intensity. My bad. Power's always the same. Power's always set. It's intensity that's doing this. Right? It's just that the power is spread over a larger amount of space. The joules per second coming out are always the same. Okay? People often, I think, confuse that, and I even confuse it or say it wrong sometimes. Power is set, but intensity, which is power per square meter, drops at a square to distance. Okay.